Okay, so I know you wanted to see some of the solutions to the Kahoot. Okay, so here I think I can show you this. Can you see this now? So it doesn't tell, okay, so Euler's method is used to solve. You can use it to solve a separable differential equation, and you can use it to solve a first order differential equation in the standard form, because we're solving for dy dx. So just put everything on the other side and then use whatever's on the other side as your f of x, y, and then you can solve it using Euler's method. Any questions about that? Caesar, were you the one that asked whether or not we could go through this?
No, it was someone else.
Okay, who asked could we go through these problems?
It was me, Malcolm.
Okay, Malcolm, do you understand that answer?
Partially, I'm gonna like look at a couple of examples to like really remember
Okay,
that.
I'll show you that example on problem one, Euler's, in a minute.
Okay, thank you.
Okay, number two, we say an improper integral diverges when the limit goes to infinity or minus infinity. So if you're trying to find an improper integral, and remember we're doing the limit as t goes to infinity, and then you put t inside the integral. If you get infinity or minus infinity, the integral diverges. If you get a number, you get 0 or a number, it converges. Okay. The first order differential equation in standard form was the first one. The second one, remember, standard form is dy dx plus p of x times y is equal to q of x. So this one got a lot of people tripped up. They saw the p of x, y equals q of x, but none of this first part was correct. The second one still had an x squared in front of, I'm sorry, the last one had x squared in front of dy dx, so that one didn't work. And this one definitely, x dy is equal to y dx plus 4 was definitely not in the right form. But the first one, p of x is just minus tangent x, and then q of x was just x squared. So that's the first, that was the answer to that one. Okay, which of these numbers does not appear in Simpson's rule? So the number 1 doesn't appear in Simpson's rule. If you remember, Simpson's rule is h over 3. So 3 appears, and then it's f of x plus 4 times the next x plus 2 times f of the next one plus 4, and you go back until you get to the last one. And since we don't write 1 as a multiplied by anything, it doesn't appear in the formula. True or false, the estimated error for the trapezoidal rule is smaller than the estimated error for the midpoint rule. That is true only because it's multiplied. It's 1/2 of the error for the trapezoidal rule. The midpoint rule is used to estimate the volume of revolution of a curve f of x, the area under a curve of a function f of x, the surface area of revolution of a curve f of x, and all of the above. You can use the midpoint rule on any integral that goes from a to b. Okay, so if you have, so any one of these are expressed as an integral, so you can use the midpoint rule for all of them. The comparison theorem is used to determine whether an improper integral is convergent. That is true. An ordinary differential equation contains an independent variable x, a dependent variable y, and derivatives only of y. It does not contain derivatives of x. So this statement is false. In a first order differential equation, y of x is represented by the second equation. Remember the c, the constant c, is very important, and it goes along with the integral, and that whole thing is divided by v of x. Okay, so that's the second answer. And then the last one I can actually do now as well. Dy dx is equal to x over y, where y of 0 is 1. That is a hyperbola. Okay, so let's go back to here. And before I start sequences, I'd like to just say a little bit about those two problems. So the first one said that you could use Euler's method on separation of variables and the other first order differential equation. So for separation of variables, you have something like dy dx is equal to f of xy. And if you remember, f of xy is either f of x times g of y, or it's f of x over g of y, or it's g of y over f of x. So either way, you want to be able to separate it. But Euler's formula says we're solving the problem that looks like this. So for Euler's formula, it's always dy dx is equal to f of xy. And so for the separable differential equation, we end up with yn is equal to yn minus 1 plus h times f of xn minus 1 yn minus 1. So you use that for Euler's equation, and if it's separable, you just make sure it's in that form dy dx. Then for the other problem, we had dy dx plus p of xy is equal to q of x. So therefore, if you put everything on the right-hand side, dy dx is equal to q of x minus p of xy, and then you call this whole thing f of xy, then you can use Euler's formula. So that's why you can use it for both of them. Okay, so that was the first question. And then the last question, we were given dy dx is equal to x over y at 0 equals 1. So this is separable. I get y times dy is equal to x times dx. So we move the dx up to here, and then we move the y up to there. Okay. So now integrate, and I get 1/2 y squared is equal to 1/2 x squared plus a constant. So when x is 0, y is 1. So I get 1/2 times 1 is equal to 0 plus c. So c is equal to 1/2. So now I get 1/2 y squared. I'm going to pull this to the other side and get minus 1/2 x squared is equal to 1/2. And if I multiply everything through by 2, I get y squared minus x squared is equal to 1. And that's a hyperbola. Okay, any questions about the doodle that we did the other day? Not the doodle, the Kahoot that we did the other day? Okay, well, I have something else planned for us today. And I have to see, I think this is how I do it. So let's first start off with what we're going to do in this next section. So in this next section, we are going to find the formula for the general term of a sequence, calculate the limit of a sequence if it exists, and determine the convergence or divergence of a given sequence. Okay. So the first thing I want to basically do is a sequence is a list of numbers. Okay, so a sequence is a list. Please remember the major word in this definition is list. Okay, these are numbers that are separated by a comma. They are a list like 252, 253, 254, 256, 503, 504. That is a list of numbers. That is a sequence. So some examples, 1, 2, 3, 4, 5, dot, 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 of course, means it keeps continuing. 1, 1/2, 1/4, 1/8, 1/16, and it keeps continuing. And 1, -1, 1, -1, 1, etc. So those are examples of sequences. Okay. So before we go on, I prepared a PowerPoint presentation. So now I just got to see how to get it to work. Here we go. Hopefully you guys will be able to see this. Okay. Okay, can you see the PowerPoint presentation?
Yes.
Great, okay. What is the next number in the sequence? Okay, write it down. Hopefully you don't need more time. What is the next number in the sequence?
-1.
Okay, you're supposed to be writing these down, but that's okay. What is the next number in the sequence? Actually, it's okay if you answer. I think that'll be good. If you got the answer, shout it out.
1/64.
Okay. What is the next number in the sequence?
$21.
21. What is the next number in the sequence?
Is it 6/7?
It is. What's the next number in the sequence?
-1/20, 243.
That sounds correct. What's the next number in the sequence?
$23.
Okay. What is the next number in the sequence?
$170.
Okay. What's the next number in the sequence?
(49√7).
That's right. What's the next number in the sequence?
$128/1701.
Okay. All right, so yes, that is correct. All right, I tried to put these in order, but I ran out of time, so we're just going to get them as they come. So that one is right. Of course, that next number was 8. This one was -1. This one was 1/64. That one was -1/243. Obviously, this is, what kind of sequence is this? Tell me quickly. Anybody know?
I don't know what it's called, but I know like how to find the next numbers.
Anybody know what this is called?
Oh, isn't that called Fibonacci?
That's the Fibonacci sequence. Yes. Okay. Now, how did you figure out this one? Did anybody have trouble with this one? Or did anybody was able to, I know one person gave the answer, so does anybody have an idea of how to figure this one out?
I do.
Okay, Peyton.
So you start from 20, then add 22, 24, 26, and 28.
Okay, that's correct. All right, this one was fairly easy, 5/6, and next one is 6/7. And then this sequence, we keep multiplying by the square root of 7, so that was correct. And this one had a constant distance between any two elements of the sequence was 4. And that's it. All righty. Okay, so we have an idea of what a sequence is now. Okay, we've done several examples of sequences. So I want to give you some more. All right, and I'm going to give these to you in sequence notation. Okay, so more examples in sequence notation. Okay, so sequence notation is to put brackets around the name of the sequence. So the terms of this sequence are AN, is when N starts at 1 and goes to infinity. So 1 is the first element, square root of 2 is the second element, square root of 3 is the third element, square root of 4 is the fourth element, square root of N is the nth element of the sequence. Okay, so we would write this as that. Okay, so this is the nth term of the sequence. All right, another sequence Bn, this is almost like the one that was in there. N is equal to 1 to infinity. So the first number is 1, second number is -1/2, the second number is +1/4, then -1/8. So when numbers alternate like that, they always have a -1 raised to the n or n-1 power. And then as you can see, this is 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the fourth. So this is 2 to the n-1. So that last term is the nth term of the sequence. And this sequence was actually in the PowerPoint, 0/1, 1/2, 2/3, 3/4. So this sequence looks like n-1/n. Okay, any questions about those? Okay, so far so good. We're smoking along here. Okay. So the notation we're going to use is just as I said here. For sequence AN, n equals 1 to infinity. Some people put it in brackets, but you must, no matter what happens, have this important ... at the end of it, because the sequence continues to infinity. So if you put it in brackets or you don't put it in brackets, you still need to have the ... because this is an infinite sequence. Okay, any questions? All righty. All right, so let's talk about convergence and divergence of sequences. Okay. So as we begin to talk about convergence and divergence of sequences, we just want to look at these two sequences. This first one being the first example that I gave. And as n goes to infinity, you can see that we start off at 1. The square root of 2 is bigger than 1, which is the square root of 1. The square root of 3 is bigger than the square root of 2. Square root of 4 is bigger than the square root of 3. And these numbers keep increasingly getting larger. Okay, so as n goes to infinity, you can see that an also goes to infinity, the nth term. All right. So actually, I'll even be more specific. I will write this as the square root of an, which is equal to the square root of n. That thing goes to infinity. So this sequence diverges. A sequence diverges when we can't reach a limit, or what we're going to consider a number that it is converging upon. Okay, that 1 does not belong there. All righty. Okay, so here's sequence Bn, and Bn is the sequence 1, -1/2, 1/4, -1/8, 1/16. So this sequence, well, what does this sequence actually look like? Okay, well, let's draw it. So let's draw the actual sequence itself. So we're going to plot the actual numbers. Okay. So when we plot the first one for A1, for n is equal, so on this down here, I'm going to list n. And then I'm going to plot Bn in that direction. So when n is 1, I get 1. So let's go all the way up to here, and we'll call that 1. When n is 2, we get -1/2. So that looks like that. When n is 3, we're going to get +1/4. So that's somewhere around here. And when n is 4, we're going to get -1/16. Positive, wait a minute, what am I doing? Something's wrong. 1, -1/2, 1/4, -1/8, +1/16. Okay, that one is -1/8. So this is n equals 5, and we get something here, and then n equals 6. So as you can see, this sequence of numbers, all right, is getting closer and closer to what value?
Is it 0?
It's 0. Okay, so these numbers are going to keep getting closer and closer and closer and closer and closer and closer to 0. Now they are going to never equal 0, but they're getting closer to 0. So this sequence is doing its very best. It is trying to go to 0. Okay, so it's trying to go to 0. So we can say this sequence converges. converges to 0. And the way we're going to write that is we're going to say the limit as n goes to infinity of the sequence an is equal to 0, where an was -1 to the n minus 1 divided by 2 to the n minus 1. Okay. So we have a definition. Something happened for a minute. I'm not sure. Let's go back. Oh, I know what happened. Okay. Okay. So here's the definition. A sequence an converges to the number L if for every epsilon greater than 0, there corresponds an integer n that's also positive, such that whenever n is bigger than n, the absolute value of an minus L is less than epsilon. If no limit exists, then we say an diverges. In order to calculate the limit, we compute the limit of the actual term an. Now, as you write that down, I'm going to explain to you what in the world does that mean. So I will show you. So I want to go back to this other picture. Where's my picture? Okay, so let's go back to my picture here. So we want to take this picture and I'm going to grab it. Okay, so for this picture here, if for this function, we said for this function b sub n, we had b sub n, it was equal to -1 to the n minus 1 divided by 2 to the n minus 1. Okay, so what the definition of the limit existing actually means. So for this, we claim that the limit as n approaches infinity of bn is equal to 0. Then for us, our L, which is the limit, L is 0. So L is 0. And if I look at the absolute value of bn minus L less than epsilon, that means that minus epsilon is less than bn minus L is less than positive epsilon, or bn is less than L plus epsilon and L minus epsilon. So here's my limit. My limit was 0. So my limit was right here. So my limit is L is equal to 0. So here is L plus epsilon. And here is L minus epsilon. So I can do this for any number epsilon. So for any number epsilon, I need to know that my function, or my sequence, I should say, is inside this. And there's going to be a certain number n for every epsilon. So as you can see, for that huge epsilon, n is 3, because it's after the third term that everything is squashed inside of there. But I can choose a smaller epsilon. So if I do L plus epsilon here and L plus epsilon here, and now this is smaller. And here's L minus epsilon. So now notice I have to go out further into the sequence until all the points are within an epsilon margin about my limit. So that's what the definition means. Okay, so I'm going to come back here, let you guys get a few more minutes to write down the definition and process that. And I am going to take the roll. Okay, so we're finished with that.
I got a question.
Yes,
When's our next exam again?
it is Thursday.
Okay.
Okay, and since you asked, let me just make a comment. It will cover 3.6 numerical integration, 3.7 improper integrals, 4.2 numerical methods, 4.3 separable differential equations, 4.5 first order linear differential equations, and 5.1 sequences.
Can you post the exam from last year?
I certainly will.
And then with the answer sheet, correct?
Will, that's what yep,
Thank you.
you're
Hi,
welcome.
do you mind going over what will be on the exam one more time, please?
Okay. From module 5, 3.6, 3.7, 4.2, 4.3, 4.5, and from module 6, 5.1.
Can you one more time, but slower, so I could write it down?
No problem. 3.6, 3.7, 4.2, 4.3, 4.5, and 5.1.
Okay, thank you.
No problem. Okay, so let's look at some examples. So here's the sequence. It is -1, -1/2, -1/3, -1/4, -1/5, ... Okay, can you guys tell me what the form of the sequence is? AN is equal to what? Anybody have an idea? A1 is -1. A2 is -1/2, okay? A3 is -1/3. A4 is equal to -1/4. So now if I go back to A1 and divide by 1, now can anybody tell me what the form of the sequence is? AN is equal to I have a 1 here and a 1 here, a 2 here and a 2 here, a 3 here and a 3 here, a 4 here and a 4 there. So I would expect if I have an N here, I'm going to get -1 over N. So that's the general form of my sequence. Okay. So now if I want to find out whether AN converges or diverges, I'll take the limit as N approaches infinity of -1 over N. I can pull the negative out. We're going to use some limit laws in a minute. The limit as N approaches infinity of 1 over N. And we talked about this. You have one pizza and you're dividing it by everybody on campus. You barely get any. That limit is 0. Okay. So we can say the limit as N approaches infinity of the sequence AN is 0. So that implies that N equals 1 to infinity converges. Okay. Let's look at number 2. Some of these can be really hard too. So I'm trying to stick with some ones that work. Okay, we saw this one. 0, 1/2, 2/3, 3/4, 4/5. And we were able to determine the next term in the sequence. So now I have A1 is 0. A2 is 1 over 2. A3 is 2 over 3. A4 is 3 over 4. So if I go back to the first one and put a 1 there, it looks to me like here's A1, 1's in the denominator. Here's A2, 2's in the denominator. Here's A3, 3's in the denominator. Here's A4, 4's in the denominator. So that gives me an idea. Okay, my OneNote is having a moment. Okay, I think we're back. Okay, so therefore, AN looks to me like it has N in the denominator. And the number above it is always 1 less. Oh, this is a B. I apologize. This is BN. And these, oh, well, they're all A's now. This was supposed to be BN, but it's now AN. Okay, and so the 1 above it is always 1 number less. So that looks like AN kind of looks like N minus 1 over N. Okay. So now we want the limit as N approaches infinity of AN is the limit as N approaches infinity of N minus 1 over N. Now there's several ways you can do this. You can actually use L'Hopital's rule. You can split the fraction, or you can divide everything by the highest power of N. So there are 3 different ways to do this limit. Whichever way works for you is fine. The easiest way is to just write this thing as the limit as N approaches infinity of 1 minus 1 over N. So just split it. We know 1 over N goes to 0. So this limit is 1. So as you keep going out in the sequence, we're going to have numbers that are going to look like 900, and 99,999 over 1,000,000. That number is in the sequence. And the number's getting very close to 1, but it'll never equal 1. Okay, so that number is a number in the sequence. Okay, so now we can say the limit as n approaches infinity of an is equal to 1. So that implies the series, the sequence, oh my gosh, getting my words messed up, n equals 1 to infinity converges. Now, if the limit goes to infinity, then it diverges. Okay, any questions? All right. Limit rules. Now, we've seen these before in Calculus 1, so I'm not going to spend a whole lot of time. Uh-oh. Oh, yeah, that's right. That's the beginning. Okay, so the beginning of the limit rules, we want to assume that we have two sequences. One is an and one is bn, and they both have real numbers, and a and b is a real number. And I want to assume that the limit as n approaches infinity of the sequence an is a, and the limit as n approaches infinity of the sequence bn is b. So I have two different sequences. Then here are our limit rules. All right, so the first one is the sum rule. So if I'm taking the limit of the two sequences, it's the same as taking the limit of the an, which is a, plus the limit of the bn, which is b. The difference rule is the limit of the difference of two sequences is just the difference of their limits. Again, I am posting all of these notes. So if you're just trying to write down the few important things, I will have, the notes will be posted so you can get the full, nice, neat copy of everything. Constant multiple. If k is a constant, and I do the limit as n approaches infinity and k is multiplied by an, then I can pull that k out, just like I pulled that minus out up top, and I just get k times the limit. The limit of the product is the product of the limits. The limit of the quotient is the product of the quotient. And what I call the denominator rule, this is not official name for it, but I like this rule. Basically, if n is in the denominator and there's more, the power of the denominator is higher than the power of the numerator, this is always going to go to 0. Okay, so let's do some examples. So, number 1, let's let an is going to be 2n minus 3 divided by 4 minus 5n. Okay, does anybody know what the limit of that sequence, that term is, so that we can find the limit of the sequence? What can I use that we learned this semester? So we want the limit as n goes to infinity of an. That's the limit as n goes to infinity of 2n minus 3 divided by 4 minus 5n. Okay, so that limit on first pass is infinity over infinity. Does that help you now? Well, it's actually infinity over minus infinity, but does that help anybody in trying to figure out what the limit is? What can you use? I might need to bring something back and put it on the test. What can we use?
L'Hopital's.
All righty, thank you, Malcolm. Okay, so we're going to use L'Hopital's rule. L'Hopital's rule says I can take the derivative of the numerator, that's just 2, divided by the derivative of the denominator, that's just -5. And the limit as n goes to infinity of 2 over -5, well, there's no n in there. That is just -2/5. Okay, so hence the sequence an n equals 1 to infinity converges to our limit L is -2/5. Any questions about that? Okay. Here's one. Let's look at number 2. AN, actually I'm gonna call it BN, is the cosine of n pi over 2. Okay, now we all know that the cosine function just goes up and down, up and down, up and down, up and down. So I'm assuming that I'm really not going to get a limit because the cosine doesn't get smaller. So, but let's just see what we get. Okay, so I'm going to plot some numbers here. Okay, so let's let n be 1 of me. Here's n, then this is going to be n pi over 2, and this is going to be the cosine of n pi over 2. So when n is 1, we just get the cosine, this is just pi over 2. When n is 2, then this just becomes pi. When n is 3, we get 3 pi over 2. When n is 4, we get 2 pi. When n is 5, we get 5 pi over 2. When n is 6, we just get 3 pi. When n is 7, we get 7 pi over 2. When n is 8, we get 8 pi. No, we don't. We get 4 pi. So I think that's good enough. Okay, that should help. So the cosine of pi over 2 is 0. The cosine of pi is -1. The cosine of 3 pi over 2 is 0. The cosine of 2 pi is +1. Okay, this is not looking real good here. The cosine of 5 pi over 2 is -1. And then, no, it's not. It's 0. The cosine of 3 pi is -1. The cosine of 7 pi over 2 is 0. And the cosine of 4 pi is 1. Okay, so this sequence Bn looks like 0, -1, 0, 1, 0, -1, 0, 1. We know the next term in the sequences and we can keep it going. Okay, so does this sequence of terms look or appear to you to have a limit? Like they're all trying to approach one number?
No.
Not at all. Okay, so these are not trying to approach anything. All right, so again, some sequences don't have limits. So some sequences don't have limits, and this one is one of them. Okay. In fact, the limit as n approaches infinity of Bn does not exist. Hence, this sequence diverges. Okay, so it doesn't have a limit. Okay, any questions? All right, so let's look at some commonly occurring limits that we are going to need to solve problems in this section. Okay, so some commonly occurring limits. Okay, number one. We already said this one, but this is very important, that the limit as n approaches infinity of 1 over n is 0. Okay. Number two, the limit as n approaches infinity of the natural log of n divided by n, it is also 0. Okay. Number three, the limit as n approaches infinity of x to the 1 over n, which also can be written as the nth root of x. All right, this limit is equal to 1, and here we're assuming x is a positive number. Number four, the limit as n approaches infinity of 1 plus x over n raised to the nth power is the function e to the x. Number five, the limit as n approaches infinity of the nth root of n is equal to 1. Sometimes you might see it as the limit as n approaches infinity of n to the 1 over n equals 1. Sometimes you may see it like that. Number six, the limit as n approaches infinity of x to the n is equal to 0 And this is if the absolute value of x is less than 1. So any fraction raised to a fraction less than 1 raised to the nth power is going to go to 0. And number 7, the limit as n approaches infinity of x to the n over n factorial is 0. Okay. Alrighty, let's do some of these. All right, so first one. Number 1, an is the sequence of terms, the log of n squared over n. Now that looks difficult. We could use L'Hopital's rule. We know we're going to get infinity over infinity. So you can use L'Hopital's rule. But if I use properties of logarithm, this just becomes 2 times the natural log of n over n. And our second rule back here says that limit as n goes to infinity is 0. Limit of n goes to infinity of an is the limit as n goes to infinity of 2 times the natural log of n over n. Now this is that constant multiple rule. It says I can pull this 2 out of the limit. So this is 2 times the limit as n approaches infinity of the natural log of n over n, and that's 2 times 0. So that's 0. So the sequence an will converge. Bn is the square root, the nth root, I apologize, of n squared. Okay, so I can fix this again, make it look like something I know. I can make Bn look like the nth root of n quantity squared by using properties of exponents. So therefore the limit as n goes to infinity of Bn is just the limit as n goes to infinity of the nth root of n squared. Why do I feel like I missed the power rule when I did these common rules? I didn't see, okay, there is a power rule that says I can write this as the limit as n goes to infinity of the nth root of n and then square that value. So that's 1 squared, which is just 1. Cn is the sequence defined by n minus 2 over n to the n power. So I can work with that. I can write that as 1 minus 2 over n to the n power. And so the limit as n goes to infinity of Cn is the limit as n goes to infinity of 1 minus 2 over n to the n. And if we look back up here, that's just the fourth limit where x is replaced by 2, negative 2 actually. So this is e to the negative 2. Any questions? Okay, so the last thing before we just do some general examples is the sandwich theorem. And the sandwich theorem says, if I have two limits and they're going to the same thing, and there's something squeezed in between them, it also has to be going to the same thing. So it's the sandwich theorem. Let AN and BN and CN be sequences of real numbers. Okay. If AN is always less than or equal to BN, which is always less than or equal to CN, for all n, when I say greater than n, I mean sufficiently out far at the end of the sequence. And it's necessarily true that the limit as n approaches infinity of AN is the same as the limit as n approaches infinity of Cn, and that limit is L. So AN is going to L and Cn is going to L, then Bn can only be doing the same thing. The limit as n approaches infinity of Bn also has to be L. So if it gets sandwiched in between. Okay. Here's an example. Determine if the sequence AN equal to the cosine of n over n converges or diverges. Okay. Well, I'm going to squeeze it between two things. So I know that the cosine is sandwiched between -1 and 1. So therefore, -1 over n has to be on the bottom limit. We're dividing everything through by n, 1 over n. Okay. Now the limit as n approaches infinity of -1 over n is just minus the limit as n approaches infinity of 1 over n. And that is 0. And then the limit as n approaches infinity of 1 over n, well, that is 0. So this side is going to 0, and this side is going to 0, which says by the sandwich theorem, because it's sandwiched in between, that limit as n approaches infinity of the cosine of n divided by n also has to be 0. Okay, so I have some more sequences for you guys to work on. We'll look at that. I need to talk about a sequence with an absolute value. I'm not absolute value, a factorial inside. All right, but that is it for today. Are there any questions?